Welcome back. We're going to follow up with an example of how to use the two-path test. In this case, we're going to look at a function where we actually have to use paths 3, 4, and 5 to really figure out whether or not this limit doesn't exist. Remember, the two-path test doesn't tell us anything about existence. It only tells us about non-existence. So in this case, we let the function f of xy be x times y squared, all divided by x squared plus 4 to the y to the fourth. And we want to know, does the limit as xy approaches 0, 0 exist? In order to solve this thing, we're going to try to analyze this from a few different paths and see what happens. Let's begin along the general path y equals mx. So this one does go through the point 0, 0 for an arbitrary slope m, which implies when I look at the limit as x comma y goes to 0, this is going to be x comma mx goes to 0 comma 0. Everywhere I see a y, I'm going to substitute that in with mx, because I'm saying that my y value is given by mx. And then now this becomes mx to the fourth. Okay, so now this is equal to what? Well, the nice thing about substituting y in terms of mx is that now this is a single variable limit. And then up top I have something like m squared times x to the third. On the bottom I've got something like x squared plus m to the fourth x to the fourth. We see that in this case, this goes back to our knowledge of Math 1a. I can factor out perhaps an x squared in the numerator and the denominator, and I'm left over with something like m squared x, all divided by 1 plus m to the fourth x squared. If I look at this limit, this ratio goes to 1, and then this goes to 0. So of course, because the top x goes to 0, this goes to 1, this goes to 0, so I've got 0 times m squared divided by 1 plus m to the fourth. So this limit is 0. That doesn't mean that the original limit is 0, because the whole idea is that the original limit will exist if and only if the output approaches a single number, no matter how I approach the input. The distance is what matters, not the path. Well, we promised that in this case we should probably consider a different path, and we'll try one of the parabolas. Let's try a different path. The path I'm going to choose comes from looking at the actual function definition quite carefully. The whole idea of choosing path is to turn a multivariable limit into a single variable limit, but we do so in creative ways. In this case, we did so to cancel out an x squared on the top and bottom so we could actually evaluate it. If I was going to do a parabola, I would want it so that there was a factor of the variable that I'm trying to isolate, or the variable I'm trying to get it in terms of, both on the top and the bottom. Notice here I have a y squared, here I have a y to the fourth, here I have an x, and here I have an x squared. If I tried to substitute y equals x squared, I would get something like x to the fifth on top, and then something that doesn't look very beautiful on the bottom whatsoever, right? I'd have like x squared plus x to the eighth. And I suppose I could pull out an x squared, but I would just get the same limit back that I got down there. However, if I did it the opposite way, if I said that x equal y squared, so along the sideways parabola, on the top I would have y to the fourth, and then I would have y to the fourth's addition on the bottom, and I could factor out a y to the fourth, a pure y to the fourth on both the top and bottom. It's going to take some thought to look at that, but that's exactly the conclusion that I'm going to make. We should really do this path along the x equal y squared parabola. If I do this, then the original limit that I wanted to take, where I was looking at x comma y, would now become y squared y, and this was going to go to 0, 0. Everywhere I had an x, I'm going to go ahead and evaluate that as y squared, because that's the path I'm on. Here I say that this is y squared squared, and then I have y to the fourth. Well, we've just transformed a multivariable limit into a single variable limit. Now this becomes y to the fourth on top, and on the bottom I've got something like y to the fourth plus y to the fourth, which of course I can use my glorious algebra to recognize this as y to the fourth over y to the fourth times 1/2, and this limit is indeed 1/2. Well, we've just determined that the function that we started with has two different values along two different paths, and we can conclude this limit as x comma y goes to 0 comma 0 of f of xy, dano dne, does not exist. And it doesn't exist because of the two-path theorem. It's actually a two-path test, it's not a theorem. In the next video, we're going to take a look at a situation where the path test does not allow us to conclude that a limit doesn't exist. If we test a function along 8 different paths and we get the same value out, we cannot conclude that the limit exists, but we can say we have a pretty strong idea that it might exist. In the next video, we'll get our heads around that. See you there.